Okay, so moving on to question 4 of experiment 10, it asks us to write the Lewis structure and 3D model of phosphorus pentafluoride, so PF5. So with this one, we do the exact same steps that we've done in the previous examples. The first thing that we have to do is determine the total number of valence electrons in the molecule. So with phosphorus, we know that there is one of them, and phosphorus is in group 5, so it contributes 5 valence electrons. Fluorine is in group 7, and there are 5 of them, so they each contribute 7 valence electrons. So when we add this up, when we are all done, we have to have 40 valence electrons drawn in this structure. Now, for this molecule, we look and we determine what is the central atom, what are the terminal atoms. And the central atom is usually written first, so in this case, we have our phosphorus, and it's surrounded by the 5 fluorines. So we've done step number 2. Step number 3 is to draw single bonds from your central to all of your terminal atoms. So we draw single bonds. Then we give our terminal atoms, in this case fluorine, an octet. And fluorine wants 8, so we need to draw 6 additional electrons around each fluorine in order for them to have a total of 8 electrons. Now, once we've done that, we count and say, okay, how many of the 40 have I drawn? And if we count them up, we see that each have 8. So we have 8, 16, 24, 32, 40. We've drawn all 40 valence electrons. So then we have to ask ourselves, okay, does everything have an octet? And if you look at this, we know that all of the fluorines have an octet. However, the phosphorus actually has 10 valence electrons. And you know that this isn't right. But remember, we can have what's known as expanded octets, where if we're in a certain position on the periodic table, we can actually hold more than 8 valence electrons. And when you can observe expanded octets is when we have in our position group 3, period 3, and below. So if you look on the periodic table, you see the phosphorus is indeed in period 3. So therefore, it is capable of holding more than 8 valence electrons. So in this case, we see that we've used all 40 valence electrons, all of the fluorines have an octet, and the phosphorus has more than an octet. So this is the Lewis structure for phosphorus pentafluoride. Now, in terms of a 3D structure, we need to again look at the phosphorus and only the phosphorus. So what we see is that there are 5 regions of electron density around the central atom. Now, the 5 regions, that gives us a possibility of having quite a few different geometries. But we have to look at it and say, what type of regions of electron density do we have around the phosphorus? And what you see is that they are 5 bonding pairs. So, what that indicates is that the geometry of this molecule is going to be trigonal bipyramidal. So, with trigonal bipyramidal, if we look at it in terms of a 3D molecule, when we have 5 regions of electron density, we're going to have a central atom, and what we're going to see is that we're going to have 2 bonds that are straight up and down. Okay? These 2, which are exactly opposite each other, are what's known as axial bonds. So, axial bonds, straight up and down. Now, we're also going to have 3 equatorial bonds. So, one of them is going to be in plane, One is going to go behind, and one of them is going to go out of the plane. So these three positions are what's known as equatorial bonds. So we have equatorial bonds and axial bonds. So for this molecule, if we draw it correctly, we have our central atom. We have two axial bonds that are flat in plane. We have one equatorial bond that is in plane. We have one going behind, and we have one coming out of the plane. So once we've done that, then we simply need to insert our terminal atoms. So we put in our fluorines. And remember, we do not have to draw the lone pairs on the terminal atoms, only the central atoms. Now, with this particular molecule, if we're looking at it, we see that there are a couple of different bond angles. Okay? So from here to here, we know that we have a bond angle of 180 degrees. From here to here, within the equatorial positions, we have a bond angle of 120 degrees. And from here to here, between the axial and equatorial positions, we have a bond angle of 90 degrees. So with this particular molecule, we actually have three different bond angles, if you will, whereas all other examples that we've seen are only contain one bond angle. So we saw with the linear that we had 180 degrees, with the trigonal planar we had 120 degrees, and with the tetrahedral we had 109.5 degrees. Here with the trigonal bipyramidal we actually have three different bond angles that we need to consider. Now with these ones, the axial positions are actually longer than the equatorial ones, and the reason is that they can spread out. We have this 90-degree interaction between the axial and equatorial position. So as a result of that, we have greater electron repulsion. So because of the greater electron repulsion, these axial positions actually end up lengthening within the molecule. So with this particular structure, you have to pay attention to how you draw the molecule in 3 dimensions. So it's very important that you draw the correct bonds that are in plane, the bonds that are out of the plane, and also pay very close attention to both axial and equatorial positions along with the bond angle.